Hi everyone. Okay, we are doing lesson 3.3. I'm sorry I'm not there with you. My surgery got pushed back a little bit later in the day and threw everything off. So everything went well, but here I am, just my voice. Sorry. Do me a favor, warm up, write these down, and then pause the video. And I want you to try and find both the x and the y-intercepts for the following exponential functions. Okay, so we're looking for x and y-intercepts for exponential functions. Do your best and then unpause the video and come back and we'll talk about what I did and in comparison to how you did, and we'll see. Welcome back. Okay, reminders for x and y-intercepts. For the x-intercept, we set 0 equal to the equation. We substitute 0 in for y. So if we look at what I did, you need to always isolate the base. So we're going to add 2 to both sides, divide by 2, and then we get 3 raised to some power is equal to 1. Well, again, if you need to write this down, do so. The first thing that you always want to check and see is if you can change the bases. And in this case, we absolutely could. We were able to change 1 to be 3 to the 0 power. The reason why we want to do this, and remember, we worked a lot on this about 2 weeks before Thanksgiving break. You have a whole handout on it. Is if I can get the bases to be equal, we then just need to focus on the exponents. In this case, we were able to do that. Easy peasy, gave us an x-intercept of 1/4, 0. Always writing our answers in equation format. Equation? No. Always writing our answers in a coordinate form. So we have 1/4, 0. For the y-intercept, we substitute in 0 for x and then simplify down. Once we substituted in 0, we got 3 to the negative first power. That gives us a 1/3. The negative exponent forces us to take the reciprocal. And then our final answer was 0, 1, and 1/3. Oh, that definitely should be negative. Sweet. So that's the first one. Okay, for our second one, same idea. We have our base, which is 1/3. We need to isolate the base. But there's a little bit of a problem when we get down here. And the problem is that I cannot get a positive base to equal a negative number. We can't ever get 2 to some power to equal -2. It's not possible. So therefore, this isn't actually an equation we can solve, and we don't have an x-intercept. For those that were with me on, I believe it was Monday, we touched base on it. Actually, no, before Thanksgiving break, we talked about how exponential functions have horizontal asymptotes that we don't cross. Why? Because you can't have a positive base raised to an exponent and then end up with 0 or a negative number. So here's another perfect example of that. For the y-intercept, again, we plugged in 0 for x and simplified down, leaving us with 0, 6, and 1/3. If you have any questions on these two, please write them down and either email me or save them for Monday. Preferably email me and I can compile a Google Doc and share with everybody. Okay? All right, so important things to remember when solving exponential equations. Whoa. Okay, one important thing. You must isolate the base. You must isolate the base before solving for x. Before solving for x. You should try to change the bases first. So we're going to try to manipulate the bases to be equal. The bases to be equal. And then if that doesn't work, then solve using logarithms. Now, for those of you that weren't with us on Tuesday, make sure you get the notes off of Canvas and or from a friend, and then touch base with me if there's gaps or questions you need me to answer or fill in. So what the heck is a logarithm? Well, let's do a little backtracking, yeah? Logarithms are the exponential inverse. So if I cube something, the inverse is the cube root. If I add two terms, the inverse is subtraction. They're operations that undo each other. So if we have a base raised to an exponent and it equals an answer. Yes, we saw this on Tuesday, but it's so good to review always. So this is our base. This is the exponent. And then we get an answer. Hopefully. Well, what is the relationship between a logarithmic equation and an exponential equation? Well, it looks like this. A log is an operation. So we're going to take the log base b of the answer, and it's going to give us the exponent. That's how it works in reverse. So the base, we say log base b of answer. And for those with me on Tuesday, remember that I said it's not log base b times a. It doesn't make any sense. That would be like saying, oh, I'm going to take the square root times 4. Huh? Square root of what? Nobody knows. Logarithm is an operation, and if you need to put it into parentheses as a visual reminder, you're more than welcome to. And when you evaluate a logarithmic term, ultimately what you're looking for is what exponent can I raise the base to and get the answer. That's your goal. Okay, so let's write that down. We haven't worked too much with logarithms in this class. You have in the past, but just so you have it to refer to, when you evaluate a logarithmic expression, or we'll just say a logarithm, you are looking for the exponent. You are looking for the exponent. So let's practice a little bit, yeah? Pardon me. Rewriting each logarithmic term into exponential form. Okay, so that's example number 1. Well, looking at our definition, we know this is going to equal some x. So if I rewrite it, the bases are always the same. So I'm going to rewrite this as 3 to the x is equal to 9. 3 to the x is equal to 9. Base, exponent, answer. Okay, for b, our base is 5. It's going to equal some exponent. So we say 5 to the x is equal to 125. Again, base grabs the exponent, it equals the answer. Okay, so if we can rewrite, well, that means we can definitely evaluate. We can find the exponent. Now, some of you will get comfortable with these and you won't have to set it equal to x. You probably won't even have to rewrite it, and that's totally okay. For the purpose of today, I am going to rewrite it. I'm going to rewrite the base to the exponent and set it equal to the answer. Now, at this point, our comfort level varies within the classroom. Some of you will see it, some of you will not. So use what we did 2 weeks before Thanksgiving break. Rewrite it. We know that 1 over 3 can be rewritten as 3 to the first. And we know that 27 can be rewritten as 3 cubed. This leads us to have a negative x equal to 3, because now, since our bases are the same, we're focusing on those exponents. So we get x is negative 3. That's what this logarithmic expression evaluates to. Now, we made it into an equation, but that's okay, because when you're evaluating a logarithmic expression, what are you looking for? The exponent. So I just set it equal to x. Let's do the same with b and see what we can find. So again, identifying the base, we get 64 to the x is equal to 1 over 32. Definitely needs some manipulation here. So let's change 64x to be equal to 32 to the negative first power, getting rid of that fraction. Options for base manipulation. 2, 3, 4, I guess. 5, 7. I like 2. Let's use 2 because I know that 2 to the 6th is 64, and 2 to the 5th is 32. This allows me to relate them, and then I get 2 to the 6x is equal to 2 to the negative 5th, leading us to then focus on the exponents. So we get 6x is equal to negative 5. Again, we're focusing on the exponents because we were able to make the bases the same. So now we have to make the exponents the same. And this evaluates to negative 5 over 6. Yay! All right, do me a favor. Pause this. Oh, you know what? Nah, we'll do it together. Okay, again, setting it equal to x. Identifying the base. So we get 4 to the x is equal to negative 16. Base, exponent, answer. Okay, so we could manipulate, right? We could change 4 to be 2 squared and then, wait a second. Think back to what we talked about at the beginning of this warm-up, right? Think back to what we talked about on the Thursday before break. Can this even happen? Can I raise a positive base to an exponent and get a negative number? Sure can't. So we're going to say no solution. Sweet. Okay, I hope this helps you get a little bit more comfortable, just these few examples. I'm going to skip over the properties for right now, and I want to go down to example, what was it? 6. And I want to solve with you because I feel that if anything or any area we struggled with in our homework 3.2, it would be the solving. So let's do some of these together. So you know what? I'll do the first 2 and then we'll jump to the properties because we'll have to. Okay, hang in there with me. So if we look at example 6a, it's exponential. First thing we need to do is identify what sort of function. This is exponential. So what do? We isolate the base. I'm going to subtract 2 to both sides. So 2 times 3 to the x minus 2 is equal to 10. What we talked about before break, you have to isolate the base before you can try to set the bases to be the same. So I'm now going to divide by 2. We get 3 to the x minus 2 is equal to 5. Looking at our two bases, 3 and 5, I can't get 5 to somehow be 3. So we're going to have to rewrite this in logarithmic form. Our base is 3. We're going to get the log base 3 of 5 equal to x minus 2. Again, the base, the exponent, the answer, the exponent. Base, answer, exponent. And ultimately what we're trying to do is solve for x. So x is equal to the log base 3 of 5 plus 2. For the purpose of class today, we're going to leave it as is. When I see you on Monday, we'll do some calculator work and we'll get the approximations. For now, this is as far as we're going to go. Okay, so remember exponential equations. First, try to manipulate the bases to be the same so that you can ultimately set their exponents to be equal. If you can't do that, we resort to logarithms. Take a look at B. Now, we didn't write down steps as far as how to solve a logarithmic equation because we didn't need to. It's very similar to exponential. We want to isolate the term that has the base in it, the log term. So first thing I want to do is add 4. We get 6 is equal to 2 times the log base 3 of 2x minus 2. Again, if you need to, write that down. First, we're trying to isolate the logarithmic term. So what comes next? Divide by 2. We get the log base 3 of 2x minus 2 is equal to 3. All right, we've isolated the logarithmic term. This is as far as we can go. What do? Rewrite into exponential form. We have the base of 3 raised to the exponent of 3 equal to the answer of 2x minus 2. In other words, the 3 base, the exponent, and it equals that. From here, let's simplify. We know that 3 cubed is 27, and that equals 2x minus 2. Adding 2 to both sides, we get 2x is equal to 29. So x is 29 over 2. Now, think about what we talked about with exponential equations. We'll stick with this. We can't come back, Surface Pro. We can't have 3 to some power equaling a negative 3, right? That can't happen. Ooh, that's my fridge. That's really loud. Sorry if you can hear that. So that also means if we were in reverse, that the log base 3 of negative 3 equaling x can never happen. That's right. You can never take the logarithm of a negative number. Wah, wah. So let's go back up to the top and write that down so we don't forget. Reason being, what we just talked about with exponentials. We can never take the log of a negative number. Of a negative number. And once again, the reason is because you can't raise a positive base of an exponent to some number and get a negative result. So the same thing, if we were to rewrite it in log form, applies. Okay, so hopefully that helps with the homework 3.2 stickiness, if there was any. Last thing I want to talk about with you guys today are the properties of logarithms. Think back to exponential properties, right? If we are multiplying the same bases, we add their exponents. If we're dividing the same bases, we subtract their exponents. Well, it's very similar for logarithms, and as you're practicing and doing your homework, make sure you have this chart handy for you. First thing, we know that a to the 0 power is 1, right? Any base to the 0 power is 1. So it only makes sense that log base a of 1 is 0. We also know that any number raised to the first power is itself, and that's where this other property comes into play. Okay, these are these first few, very common sense, but it's good to address them so that we know. If we take a look at the third one down, this is similar to if we had a to the m times a to the n for exponential. That leaves us with a to the m plus n, right? It's the product property. So for logarithms, if I have the logarithm base a of a product, I can write that as the log base a of the first number plus the log base a of the second. And it's important to note that you can work in both directions, and I'll show you that in a second. Okay, so if I have the log base a of m plus the log base a of n, you can condense them through multiplication. The most important thing you have to pay attention to is that the bases are the same. Okay, and that follows with the fourth property also. If I have a to the m divided by a to the n for exponential, that's the same as a to the m minus n. Always the numerator over the denominator. And again, I feel like I'm repeating myself, but it's so important. We talked about this 2 weeks before Thanksgiving break, and y'all did really, really well in remembering. So if I have the log base a of m divided by n, I can rewrite it through division, keeping the bases the same, making sure that it's the log base a of the numerator subtracted by the log base a of the denominator. And you can work in both directions. So if I have two logarithmic terms whose bases are the same and they're subtracting, I can condense it through division. Pretty snazzy. Another one we're going to use a lot is the power property, and it states that if you have a logarithmic term raised to an exponent, that exponent can be rewritten as multiplication in front. Yep, if I have a logarithmic term where I'm taking the log of a number raised to an exponent, I can move that exponent in front of the logarithmic term through multiplication. And we can work both ways. So I can also rewrite it. If there's a number being multiplied in front of my logarithmic term, I can bump it up to the top. This should be review, and I'm sure some of you are like, oh yeah, I kind of remember that. Sweet. I hope you do. If I have, oh, this is a good one. Are you ready? Okay. If we have 3 to the m is equal to 3 to the n, right? Our bases are the same. We know that we can just set the exponents to be equal, right? Well, check this one out. If I have the log base a of m equal to the log base a of n, yep, bases are the same, we can simply focus on setting the quantities equal to each other. That one's really helpful when solving equations. Okay, so you might want to double star that one. And then the last one I want to talk through with you before we play around with them is the other direction. If I have log base a of m equal to log base a of n, then we focus on m equals n. Just a repetition, different order. All right, let's do a few and then you guys can start your homework today. There's different properties we should use first when we're expanding versus when we're trying to condense, okay? So when you're expanding, the first property that you always want to see if you can use is the power and the quotient property. You want to use, the product and the quotient property. You want to use the power property last. So if we look at A, I see that there is a fraction. So that means I'm going to use the quotient property and I'm going to say that the log base 5 of 125 is being subtracted by the log base 5 of the quantity xy. Notice I had the numerator first and then the denominator, and I kept the bases the same. That's really important. You always have to write out the bases. But we're not done, everyone, because I can use the product property for the quantity that's being multiplied together. So I'm going to say minus the log base 5 of x plus the log base 5 of y, and this whole quantity is being subtracted. So be very careful. I know I say this a lot too. Be really careful with your quantity symbols with your parentheses. All right, let's keep going. I'm going to say the log base 5 of 125, and we're going to distribute that negative. So minus the log base 5 of x minus the log base 5 of y. All right, I don't see any more quantities. So you always need to ask yourself if there are any more quantities. You always need to check for exponents. Do we need to use the power property? Here we don't. And then the last thing, definitely write this down if you need to, is you need to see if you can evaluate any logarithms. I see one. I see the log base 5 of 125. To evaluate, I need to figure out 5 to what number is 125? Ah, it's 3. So yes, before you finish expanding, and again, write this down if you need to, you need to check and see if you can evaluate any of the logarithms. Sweet. So writing out the rest of the expression, we've expanded through subtraction, we've expanded through addition, no power properties, and then we evaluated the logarithmic term. Nice work. Okay, well, there's a lot going on over here. Let's take a look. There isn't a base, and we briefly talked about this. So if there isn't a base, that means that we're in base 10. And again, we'll talk more about with that with the calculator on Monday. So let's write this out. They're all being multiplied together. So we're going to have the log of x squared plus the log of y squared plus the log of z to the negative first. Nice. Now there aren't any quotient properties to use, so the next thing we'll check is the power property, and that's this one right here. Are there any exponents we can bring to the front? Yeah, there's 3. So we're going to say that this is 2 times the log of x plus 2 times the log of y minus